Hello, welcome to Engineering Mechanics Statics, Chapter 6, the analysis of structures, specifically trusses, frames, and machines. Okay, what are we going to talk about this chapter? Well, this chapter is actually pretty straightforward. We're going to introduce the concept of structures. So for the equilibrium of structures made of several connected parts, we're going to break down and we're going to finally consider internal forces as well as just the external forces. In the interaction between the internal forces and connected parts, this whole concept of Newton's third law, right, the equal and opposite, that says that the forces of action and reaction between bodies in contact have the same magnitude, same line of action, and opposite sense. In other words, the forces are equal and opposite. So when you have a member like this and you start breaking it apart, the force that it applies to this member is equal and opposite to the force that's being applied to that member. There are three categories of engineering structures that we're going to consider. The first one is trusses. Now, trusses are formed by two force members or straight members with endpoint connections. That's a typical truss. We're going to talk about frames, which contain at least one multi-force member, which is a member acting upon by three or more forces. And we're going to talk about machines. Now, frames and machines are very similar. The difference is that machines are structures that contain moving parts and are designed to transmit and modify forces. But we're going to find the analysis is basically the same. Okay, so let's get started. Trusses. Let's talk about some definitions. A truss consists of straight members connected at joints. No member is continuous through a joint. Okay, so looking here from A to B, this is not one member. There's a member from A to D and a member from D to B. So there's no members continuous through a joint. Most structures are made of several trusses joined together to form kind of a space framework. So each truss carries loads which act in its plane, which means that we're going to treat these things as two-dimensional structures, which makes life a lot easier. We only really have to deal with the 2D aspect of trusses. Now, bolted or welded connections are assumed to be pinned together. So, we have here, these are bolted or welded or both, right? And we're going to analyze them as pins. The difference is that this type of connection could resist moment. A pin does not resist moment. Okay, so we're going to and analyze these as pins. Only two force members are considered. So in other words, this load here cannot be applied here. This no longer becomes a truss. Now when forces tend to pull members apart, it is in tension. When the forces tend to compress the member, it's in compression. Okay, so when something is getting stretched on, pulled apart, that's considered tension. The other is compression. You're going to have to keep track of that. It's going to be something that's going to come up throughout the chapter. A couple more points. Members of a truss are slender and not capable of supporting large lateral loads, which again goes to the thing if we're going to deal with these things as even here you have a truss that has kind of a third dimension to it, right? We're going to only deal with the 2D aspect of it because we're going to say it can't support lateral loads. And the loads must be applied at the joints. So again, going back to the previous slide, this load has to be at this joint. It can't be off in here or else it's no longer a truss. So these are just some examples of some known trusses that are kind of pre-designed trusses, the Pratt, the Howe, and the Fink and whatnot. These are all just trusses. So this is one of those things that civil engineers, structural engineers do a whole lot of work with. It's very well understood. Okay, let's talk real quick about simple trusses. A rigid truss will not collapse under the application of a load, right? So here you have this thing. You put loads on here and it's not going to deform, right? Whereas if you have this truss, you start putting a load on here. Remember, these are pins. These don't resist moment, so everything's going to start moving. Okay, fair enough. So what is a simple truss? A simple truss is constructed by successively adding two members and one connection to the basic triangular truss. Okay, so we start with this nice little this triangular truss. It's a rigid truss. We add two members, and one joint. And so this is considered a simple truss. What about this one? You'll notice these are both triangles. This one is not a triangle, right? This is a different shape. This is still a simple truss. So let's start with this rigid truss, right? We had 1, 2, and a joint. Here we had 1, 2, and a joint. Here we had 1, 2, and a joint. And then here we have 1, 2, and a joint. And so this is still a simple truss. And it's still rigid, right? You can apply forces, it's still not going to change. It's no longer just a simple triangle, but it's still not going to change. In a simple truss, the total number of members, we're going to call it M, can be found by the simple equations. M is 2n minus 3, where n is the number of joints. So how many members are here? Well, you can go through and count the joints. So 1, 2, 3, 4, 5, 6, 7 members. So 2 times 7, 14, minus 3, it's 11. So you're going to find that there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 members of the truss. Okay, now to the important stuff, the analysis of the truss. So there's two basic ways to analyze trusses. This first way that we're going to show you is the painful way, but it's important that you know it because, quite frankly, sometimes you have to do it. If you can avoid this method, avoid this method. This is a lot of work. It's not terribly hard. It's just a lot of steps, a lot of opportunities to make kind of a little mistake here or there. But it is absolutely necessary for some things, and this is called the analysis of truss by the method of joints. Okay, so what are we going to do? We're going to dismember the truss and create a free body diagram for everything. We're going to go through and start creating all these separate individual free body diagrams. But remember, these things are related, right? So the two forces exerted on each member are equal and have the same line of action in opposite sense. So you'll notice that this force right here is going to be equal to that force. This force is going to be equal to that force, and so on. Forces exerted by a member on the pins or joints at its ends are directed along the member and are equal and opposite. Conditions for unknown, what is the saying? Saying that you can solve for, at any point you can solve for two unknowns. And you have the conditions overall, the equilibrium of the whole thing, which makes it possible to solve for all the unknowns, the two unknowns at each point, but also the three unknowns at the overall, treating it as a rigid body overall. So let's do an example of this. This is example 6.1.